This is the design and optimization of a hybrid energy production farm using UniOps 1 experimental data, and it's by Alex, Alan, Sean, and Nikita. Our hybrid farm uses both thermal power and hydroelectric storage to generate electricity and store excess energy for later use. This addresses the challenge of having access to reliable electricity at all times, as it maintains grid stability during peak demand. Our objectives were to use flow, pump, heat exchanger, and conduction data to support the design of our hybrid pump storage and thermal energy system, and to use these to help evaluate operating conditions that balance energy efficiencies, safety, and sustainability.
Here we have the UniOps 1 experimental toolbox. First experiment is fluid flow, used for optimization of piping. We have the flow characteristic curves experiment for estimations of pump head and required power. The heat exchanger module is used to model boilers and condensers in the system, and the conduction module is used for material selection for exchangers and pipes. Here are two generic images showing common processes of both thermal and hydroelectric plants. This diagram demonstrates how they both work to efficiently generate energy that ends up in the same transmission lines.
During the fluid flow experiments, we were able to determine how pipe diameter, material, and internal roughness influence pressure losses and overall hydraulic efficiency. Our results showed that larger and smoother pipes produce significantly lower pressure drops, while smaller or rougher pipes required much higher pumping power to achieve the same flow rate. This analysis informed our recommendation to use large, smooth piping to optimize performance.
The main challenge of our hybrid system that pertains to the experiment Kerr is the pump storage aspect of the hydroelectric plant, as it needs to overcome the elevation change and pipe loss. We used the data about maximum head heights attained in both series and parallel pump setups to see which configuration would be best for our system. From the graph, we can see that the series produced a larger head height, so we recommend to use series pump configuration, assuming that pumps are used similarly to the ones that were in the experiment.
Here we have the heat exchangers module. Heat exchangers are a vital part of thermal plants as they use boilers to convert the heat energy into electricity and then condensers to recycle the steam after the end of the cycle. Optimization of these heat exchangers is essential for reduction of energy loss. So in this graph here, we can demonstrate that there are similarly high heat transfer rates for both plate and shell and tube heat exchangers, especially in comparison to the others. High flow rates and increased temperature differences are also shown to overall improve heat transfer. The recommendations that we can give to a thermal and hydroelectric plant based on these results assume well-insulated heat exchangers with minimal fouling, and we would recommend that either plate or shell and tube heat exchangers be used based on the specifications of the system, and maximizing a reasonably high flow rate and temperature difference to overall improve heat transfer and thermal efficiency.
So now we have the heat conduction module. So in this experiment in the lab, we learned about thermal conductivity, which plays a big role in the material selection that will be used in the pipes and heat exchangers in our hybrid farm. So for the heat exchanger walls, we're looking to use materials with higher thermal conductivity so that heat can transfer efficiently while still providing adequate durability and corrosion resistance. However, for pipes, the priority is a little different. Durable steels for strength and longevity are more important, and then you can control heat loss with insulation. So based on this chart from our con memo, out of the materials we used, brass was proven to have a higher thermal conductivity than stainless steel, both theoretically and experimentally. So based on this, we can recommend that, assuming insulation and no fouling in the heat exchanger walls and pipes, brass would be a great option for the heat exchanger walls because of its conductivity and strength. And then pipes, although stainless steel costs more, it would be better based on its durability and environmental friendliness.
This diagram shows how UniOps experiments inform key design choices in the hybrid pump storage and thermal system. The thermal loop uses high U exchangers as determined by Hex and suggests using brass from the con experiments to maximize heat to electricity efficiency, supplying power to the generator. That same generator drives the loop, where Kerr data supports pumps in series for high head, and Flume data identifies large, smooth pipes as the most efficient for minimizing pressure loss.
Lastly, we have the lifelong learning and professional impact. So Unit Operations 1 strengthens our troubleshooting skills by teaching us how to identify whether unexpected results came from the experiment, the equipment, or the assumptions we made before doing the experiment about conduction and flow relevant to the components in our hybrid energy system. Working with uncertainty and best efficiency points in heat transfer and pump data helped us practice realistic engineering judgments, which is vital for improving efficiency and reliability in power generation systems. And lastly, this project reinforced that engineering requires balancing safety, cost, and sustainability, showing how lab data can meaningfully guide decision choices for larger scale energy technologies. Thank you for watching.